So this is a histogram of this comes from executing the matplotlib command hist for the array sloping, and you can see it's as I said, it starts off at the top at 110 with one size, and it goes down to the bottom at roughly half the size. And I chose the number 42,000 so that I got roughly the right number of events here, because I want to get something that looks like the real Higgs discovery. Because I take these 42,000, this normalization of 42,000 will give me roughly the right number of events as background. Just to point out that you do have to run these experiments for a long time, which is non-trivial because it costs whatever it is, $500 million a year to run these experiments. Here's what happens if you take that same sloping distribution. Instead of running with 42,000, you just run with 420 events, namely 1% of the data sample. So if that data, say, took a year to run, this is what would take 3 days to run. And you can see it's pretty messy, namely. And we'll learn that when there should be 30 events, which is roughly the right number here, we would expect fluctuations of order the square root of 30, which is something like a little over 5. And so these things are oscillating back and forth pretty significantly. The error here is around 5, and here it's around 16 events, where the error is 4. So you have very serious errors, and so you would not see anything to discover a Higgs after the first 3 days of running. So that points out that this is hard. Well, you take your data and then you have to be pretty certain that you don't jump to conclusions, because you will not get enough data from a small run to reach any significant conclusions. You have to accumulate data over a long period of time. Now we get back to not the 1% sample, but the full sample. So if we had no background, we would get these beautiful plot histograms here. So this is the typical histogram of the array I call Gauss. And you can see there's a very striking peak. Total number of events here is 300. In any one, we have here the data. Notice that's 100 events. The square root of 100 is 10. So that's quite a few fluctuations. I point out later that when you run Python, you will not get the same answer as I show here, because Python uses a random initial value, namely uses the time of day to generate the so-called initial random number. And as you will run at a different time of day to me, you will never get this answer here. If you want to get the same answer in a reproducible fashion, you have to explicitly set the so-called seed for the random number generator. We'll mention this little later on. But anyway, this is a beautiful peak. However, here's something a little more the real experiment. Namely, we have here some emulation of what that Higgs experiment would see. We have here the Higgs enhancement shown added onto the sloping background. Here is what it actually looks like down here, and it's a rather modest enhancement, which has to be discovered with a detailed analysis. So this is the same plot as before, but I put on the errors. These are these estimative errors, the square root of the number of events. And so you can see that this is not a huge enhancement. Probably 2 GeV is actually a little pessimistic, and the actual width is a little smaller than that. But this is meant to give you an idea as to what's going on. Even if we had here's sort of not quite as bad as before, not 420 events, is actually a 10% experiment. This corresponds to running for a month, given the whole thing ran for a year. And you can see here the errors, and you can see that this is not good enough. The enhancement due to Higgs is comparable to the errors. So this is sloping with 4,200 events, not 42,000 events. And Higgs is just a total of 30 events, not 300. Here is back to the full data sample. And this one here is a much more striking enhancement. This corresponds to taking that narrower Higgs with a width of a half a GeV and superimposing on the same background as before. Here's the Higgs. Here's it added to the sloping background, and here's the sloping background. Now this is not a little dramatic, but if our error was half a GeV, we didn't actually do quite the right histogram. It would be better to do this histogram with somewhat smaller bin size. And so here's the same data, but plotted in 1 GeV bin, so twice as many bins. And you can see the Higgs is very clear now because we have the Higgs, we have more particles per bin relatively in the Higgs compared to the background, because we've halved the background by halving the bin size, but the Higgs are still dominantly just in 2 bins. And here is perhaps an even more striking result. This is, although not drastically so, but this is the same narrow Higgs, but we've used half a GeV bin size, not 1 GeV, or in 2 is what the original plots were. This points out that when you're doing this type of analysis, you need to think carefully about the bin size. If you make the bin size too small, you'll get too big an error, because you would have fluctuations. If you make the bin size too big, you may wash out a signal which is present if you go to a smaller bin size. So this is the type of thing an experienced physicist would do in analyzing this data. They would try to understand their measurement error, what the right bin size is, and make these trade-offs. And they would tend to do that intuitively because they've been doing this type of work for a long time.